New.
I'll give it a couple more minutes to let people filter in. That should be the transcription. So I wasn't able to upload the previous navigation recording because it was 2 and a bit hours long, because we had people jumping in and out at different times. So if you follow the link that's in the announcements, kind of the first reply to the announcement for tutorial session 1, there's a link to a Zoom site which will allow you to watch it online. But any problems with that, if you email me, I'll just put my email in the chats for now. And again, any email questions you have sort of in the meantime, you can send them to those. I'm going to arrange a cutoff date for those though. So it'll probably be the last week of lectures, just because there's 230 students on the course and I'm the only TA. It's going to be difficult for me to be able to respond to last minute questions kind of before exams. So make sure you get your questions to me before the end of the semester, kind of teaching wise. I'll give it 2 more minutes and we'll start at 5 past. Found it? Fantastic. Again, for those that just joined us a little bit later, the recordings, I'm not going to upload them to Moodle because they're too big, but I post the link to watch it online on the Zoom site underneath the announcement for the tutorial session. So this the tutorial session 2 announcements will have a message under it tomorrow at some point with the link for the recording. There was a bit of a faffing about last time because I think I had to set a password or something, so I've made sure to disable that. So you should just be able to access it straight away. And those should be up for the remainder of the year, I believe. I think someone's not muted. Right, it looks like everybody. It's going to make it. Right, hi everyone. This is going to be I'll try and speak a little bit slower. Yes, I'll try that, Abdullah. So this is the second tutorial session for Navigation Systems 4. There are going to be 3 more. One on integrated navigation, one on satellite. They're the 2 remaining topics, and then one sort of final sort of exam prep questions as well that I'm going to arrange. So the next one will be in 2 weeks' time, the same time slot. Okay. Now, inertial navigation, which is the topic we're going to cover today, is very proof heavy. All of the questions you'll find in the tutorials and in past exam papers are kind of based on proofs. So everything is in the notes. Can you mute, please? I'll mute you. Thank you. So it's very proof heavy. So we're going to go through a couple of them today, and we're just going to highlight sort of things that you'll need to know that probably will come up in the exam. Additionally, since the last tutorial, the exam structure has changed. So rather than being selecting 3 questions from 4, 1 question from each topic, it's now just going to be 3 questions that you have to do all 3 of. Okay. So I don't know the format of it, whether they're going to be on just 3 topics and 1 topic's not really covered. I suspect that there will be elements from each of the 4 kind of topics of the course, with kind of part A, part B questions. Okay. Right, so I've selected a question from 2018, which has 2 aspects that we're going to kind of cover. And then I'll go through one of the sort of longer proofs for the navigation equation. I think I'll do the Earth-centered, Earth-fixed form. But if everyone wants me to do the navigation one, the NED frame version, I can go through that as well. You should have covered that in the notes already. And again, the proofs are in the notes. I'm just going to add in some extra steps so that you can sort of help understand it a little bit better. So the question that we're going to be looking at, is that sharing? Someone just give me a yes in the chat if it is. Yeah, well, I'll go back then, 2 secs. So this is the question we're going to do today. We're going to start off with part B. Again, it's one of the shorter proofs. That's why I thought I'd go through it, just so we can get through more content. And then I'll briefly cover part A, which is going to be sort of sketching the block diagrams, which you'll see in the notes for the kind of Earth-centered, Earth-fixed navigation equation, and then the local geographic or NED equation as well. Okay, but the first question we're going to start off with is for the laser gyroscope. So there are 3 proofs for inertial sensors that you're going to need to be able to derive. So the first is the accelerometer. The second is the mechanical gyroscope, and then we're going to do the laser gyroscope. Okay, so make sure that you've learned those and you go through them all. 2 seconds, just remember I need to log in on my tablet as well. 2 seconds while I get the sharing sorted. We'll overrun, it's fine. I'll stay a bit longer just to make up for that. Laptop died. So the principle that the laser gyro works on is called the Sagnac effect. Basically, you use an interferometer to measure a phase shift between sort of two, so say two sine waves that have a kind of shifted along. And generally, we want to output an angular rate that we can calculate from that. Okay. Just sharing now. Okay. So this is kind of the diagram roughly of what a lasering gyro could be. Generally, the bigger the inertial sensor you get, the more accurate it's going to be, or less susceptible to noise and things like bias and drift. And we want to be able to get the angular velocity theta dot from this laser gyro. So the way it works, we use a beam splitter to send a wave both ways around kind of an optical circuit, a circular optical circuit. And by definition, one of these beams will get to the interferometer faster than the other because there's this slight angular velocity in one direction. So we're going to actually, we've named them actually CT plus and CT minus. So again, this is going to be very similar to the notes. So I apologize if it's quite basic for this tutorial. But we're going to first define our counterclockwise signal as CT plus. So C, the speed of light, and T being our time taken in one direction. And then we'll also do, I'll do it a little bit further down, our clockwise one, which is going to be CT minus. The reason why we do plus and minus is that angular velocities are generally measured with the counterclockwise rotation being positive. So that's why we do it this way around. Okay. And this distance really is equal to the typical kind of rotation. So C pi, 2 pi r kind of radius, and then we add r theta dots, and then T plus again. Okay, and similarly, we do the same for the clockwise signal, which is 2 pi r, except this time, because the angular velocity is acting in the opposite direction, we're going to subtract that and T minus there. Okay. Now, to get them in the form we want to get all of our T's on the correct side. So we're going to do a little bit of sort of matrix or multiplication. So I'm actually going to multiply everything by C. So I'm going to get C squared T plus is equal to 2 pi C R plus C R theta dot C plus. And collect terms. So at this point, I'm going to get CT plus, taking this one over. C minus r theta dot equal to 2 pi CR, and then dividing through, we get CT plus CR. Okay, so that's the first one. And I'm just going to do exactly the same, but for the opposite signal, which is going in the opposite direction around this optical circuit. Just to save time, I will skip to the final answer, but you'll probably be able to do this in your head. It's going to be same numerator, and then at the bottom, we're going to have a plus instead of the minus there.
CT is a distance, right?
Yeah, CT is a distance. So c is the speed of light, and time is just the kind of the delta time, the time it takes to get around the circuit. Okay.
Like, why did you multiply by C again? I mean, the whole equation would be also calculable even without it.
Just for ease of calculating it, again, you don't need to do that. It's just getting CT on its own, and because up here,
we want a distance.
Yeah, here we didn't have a CT. We're trying to keep it in form of CT. Again, if you want to just get T plus and T minus on their own, that's fine. It's just kind of adding an extra step later on. So again, doesn't really matter how you get to these 2 points. Now we want to work out the kind of the difference between these two distances we just calculated. So we're going to call this term dl, and that is equal to CT plus, which is one distance, minus CT minus, and we can just take those C's out and get this term here. Okay. But now if we sub in the two equations we got here, so we've worked out what CT minus and CT plus is. So again, this is kind of how I said you can just calculate T plus and T minus if you want, rather than CT. Again, it doesn't really matter. All we're going to do is minus 2 pi CR theta dot. Okay. And then we're going to do a bit of expansion just to get a common denominator for those. So first we'll take out the 2 pi CR term, and that'll leave us with okay. Then we'll cross multiply. Again, just getting a common denominator. So this side we'll get C plus R theta dot, C minus R theta dot. Okay. I might skip a couple of steps just to get through it a little bit quicker. But again, fairly simple algebra just to cancel this down. And at the bottom we get C squared minus R squared theta dot squared. Okay, just by expanding and cancelling there. In the chats. Okay. Now this is kind of one thing you'll need to kind of remember to do. Fairly self-explanatory. So if we look at the denominator here, we have a C squared term, and then we have R squared theta dot squared. Now we can say that C is much greater than R theta dot, just based on that C is in the order of times 10 to the 8 speed of light, whereas the radius is going to be fairly small and the angular velocity is going to be not going to be anywhere near the speed of light. So we can basically cancel this, go to 0, just ignore it, because the C squared is the dominating term in this equation. Okay. So that leaves us with dl is 2 pi CR. And then now in the brackets, we've got 2R theta dot over C. I've cancelled the C there before, haven't I? No, C squared, sorry. Getting ahead of myself. And then cancelling, simplifying this gives us dl is equal to 4 pi R squared theta dots over C. So that's the first bit we're going to need. So you can see we've got theta dot there, so we can just rearrange to get that in terms of the speed of light and this sort of delta distance. But that's not what the interferometer measures. The interferometer measures a phase shift. So again, if we imagine kind of two sine waves, very bad sine waves, but kind of one shifted, the interferometer is measuring this, which we call d phi. Okay. So therefore, we need to be able to get theta dot in terms of d phi, d phi. Okay. So there's a really straightforward equation for that, relating the distance to the wavelength, phase shift, and we have a 2 pi factor in there. Okay. Now, if we set those equal to each other, so we've got equation 1 and equation 2, we now have all the terms we need. Just do so rearrange to get our angular velocity there that we're measuring from our laser gyro. Okay. So take that up, c lambda d phi is equal to 8 pi squared r squared theta dots, and then rearranging, we get our final value. Okay, so that goes through how to derive the angular velocity for the laser gyro. Now, the mechanical gyro and the accelerometer are the other two sensor proofs that you're going to need to learn. They do come up quite often on past exam papers. I just did this one just in the interest of time to go through it. Excuse me. Okay. So if we go back to our original question, the second part of this is looking at, it's looking at the, so the first part, sorry, is wanting to derive or draw the block diagrams for the navigation equations and how the inertial measurement units of IMU, so accelerometer and gyroscopes, are used to generate and estimate attitude, position, and velocity. So these, again, are in the notes. I'm going to draw kind of one, just to kind of go through what blocks there are and what is needed, which should help with you trying to sort of remember when it comes to the exam. So we'll do the Earth-centered inertial form of the navigation equation first, just because it's a little bit simpler. Basically, we're going to have, from our previous time steps, which I'm going to denote with a minus, this is generally kind of used and known as a priori, which means sort of previous estimates or measurements. We have our direction cosine matrix or orientation for the body with respect to the Earth-centered fixed frame. Additionally, we have our previous velocity with respect to the ECA EF axes. And finally, the position. So in both of these diagrams, we're going to have our basically previous time steps or inputs on the left-hand side. And then our outputs are going to be below. And again, we can write out what our outputs are going to be. So we're going to have what's known as the a posteriori, or the plus. So the next time step, as you say, kind of once you're using the Kalman-Filter algorithm to output the estimates, this is kind of the next time step that we're going on for. Okay, and then again, we have our velocity, and zoom out a tiny little bit, our position, both pluses. Okay. So this is how you should probably try and start to structure these diagrams. Again, you can just memorize them, but it helps to kind of know where the flow of information in signals in this diagram. So we also have our sensors. So our two sensors we use in our gyroscope and an accelerometer. So does anyone remember which, I'll put them down, but which frame or what our gyroscope and accelerometers measure? It's probably a bit hard to write it in the chats. But especially for the previous mathematics section, yep, so inertial perfect. So body measures body angular velocities or accelerations resolved in the body frame, but with respect to the inertial frame, yeah. So I just remember them as, oh, that's terrible, as bib for both of them. where F is currently the specific force, not the acceleration. So that's something key to note. Accelerometers measure a specific force, which they convert to an acceleration. Okay. So we have all these inputs. I'll just put some arrows on them. I'll leave those for now, just because we're going to be drawing some blocks in a sec. But there are four kind of key blocks that are going in these diagrams. So the first is our attitude updates. So I'll call it update attitude. Okay. And then we have, given that we're measuring our specific force, we need to transform that into the correct frame, because we measure in the bib frame, so the inertial frame, but we want to transform that into the ECEF frame. So again, this second block is called transform specific force. Okay. So to update our attitude, we need to update our velocity. So I'll put that here. So again, in the previous exam papers, these have been probably worth 5 marks, just for knowing the diagram. So really easy to just kind of learn and replicate in an exam. And then finally, we want to update the position. And they're our main blocks. Okay. So again, all you need to do then is look at where the information is going. So our previous attitude is going into the update attitude, and we're using our angular rates measurements. So again, using the sort of skew symmetric matrix form to update our attitude. Again, once it's been resolved into the correct frame. And that can be outputted straight to our posterior output. The velocity again is updated. Same for position. So the other signals we now need are going between our transform for the force for the accelerometer into our velocity. And currently we're in the body inertial frame, but we need to go into the ECEF frame. So we're going to go here and we're going to label this as now EIB. Because now that's now been transformed to the specific force in the ECEF frame, which is what we need to update our velocity. Updated velocity goes out. And then finally, we need to feed that velocity back in also to the position. And then basically that just goes through some sort of integration routine. So you could use Runge-Kutta. It's probably the most popular Runge-Kutta for, but there are loads of different kind of methods to do that. But that gives you the ECEF kind of architecture for the navigation equation, is the ECEF frame. Okay. I'll give a couple of seconds just so you can scroll back in the future and sort of screenshot it for your notes. Okay. Then we're going to move on and do the local navigation frame, so NED. The main thing to take away from these though are we're using the exact same blocks. So all of these blocks are going to be, see if I can cut and paste them actually. And there's some other people in the waiting room, I think. Those people in. Okay. The only difference here is that we're going to be get rid of all these signals first. Okay. But also the positions. I'll explain why in a sec. Put the box back. Okay. So to start off with, we're now in the local navigation frame. So I'm going to need to change, I'm just going to remove all these and write them again because we're going to have to change the notation anyway. But rather than using the position estimate now, we're using sort of the longitude, latitude, and altitude for our position. Because of the NED frame, again, as the Earth is spherical, our frame is constantly rotating round. So at the equator, it would look something like this. but then at sort of 45 degrees, it's rotated round. So that's why we use sort of the latitude, longitude format for this. So again, we're now estimating the local frames. That's why it's body with respect, sorry, the body to NED axis or frame. So that's why we have the kind of B to N. The velocity, again, we're resolving in the navigation frame. And then rather than our position, we're going to use the longitude, latitude, and heights. So I'll just combine that into one signal. Okay. And same as the last time, I'm just going to bring those down and do the outputs as well. So these are our updated positions. So a posteriori, rotation, minus there, velocity, and then again, we're using longitude and latitude and altitude. Zoom out so we can see the whole diagram again. And again, our measurements, whenever you use an inertial measurement or sensor, you use the same, you measure the same variables, so we can keep those exactly the same. Like before, we can draw across our body rotation, but we also need to add in the velocity because we're now no longer resolving in the Earth-centered Earth fixed frame. We're doing it in the NED frame. So we need to take all of this information and to update the attitude. Okay. Again, we can take this across and similarly correct our specific force. So now previously we were in the, we transformed it into the Earth-centered Earth fixed, or resolved it into the Earth-centered Earth fixed frame. We're just going to do it into the local navigation frame again. And that should be IB, if I remember correctly. Okay. Velocity similarly just goes into update velocity. We don't need to add in any position data for this. One thing I did forget actually in the last one was the gravity model, which goes into the, so there was a slight mistake in the previous one, I apologize. We have a gravity model, well I remember it, which we look at as so the acceleration due to gravity, so GEB. Here it's GNB. Okay. And similarly, we're going to feed into the position with some sort of integration. Velocity update is going all the way down, and then our position takes our previous longitude, latitude, and then integrates the velocity to get there. So sorry that was a bit messy, but I hope I've just highlighted the key kind of similarities between them. Again, these are worth 5 to 10 marks, so it's really worth learning them for the exam. And as I said, the majority of the variables are similar and the blocks are similar in the middle. Okay, just a few little notation changes that need to happen. Okay.
What about the CBN plus?
Oh, sorry, yeah, forgot about that one. And that just goes straight down. So the only difference is that we need extra information to compute the attitude there, which is why we have, because our attitude depends on the altitude we're at and also the longitude and latitude coordinates on Earth, because we're going to get different sort of acceleration due to gravity there, different Coriolis accelerations. Okay. So that'll give you the final one. Again, this isn't a much neater version, is in the notes. So again, learn from that. But again, that was more to highlight the kind of key similarities between the two, between Earth-centered, Earth fixed, and the NED navigation architectures. Okay. Right. I'm going to go on to the kind of bigger derivations you're going to need to sort of learn. So these are the velocity navigation equations in both the Earth-centered, Earth fixed, basically the maths behind each of these block diagrams, So the Earth-centered Earth fixed, and then also the NED or local navigation. So I think I will do the local one, just because it's a little bit longer. So we'll do the NED nav equation. And just so you can see what a question would look like, again, this is the Got Work solution tutorial as well for this, but just so that we have a look at what it would look like in an exam, if it potentially came up, I'll share. Okay, so typically this is what you'd get if you had to do a proof question for the local navigation frame equation or NED axes. So we're given the navigation equation at the top, which there'll be some little tweaks we need to do to it. But it's basically a proof, and we need to show that we can get the local navigation equation in the form that's listed below. Now this form might change slightly, but I'm going to work through it step by step, which the tutorial solutions kind of skip over a little bit, to make sure that if a different format of it came up, you'd be able to work out what you need to change to get there. Okay. So again, I've written down the key information here. I'll just minimize this if possible. There we go. So again, we have our what was stated as our navigation equation at the top. We've been given an acceleration component here for the body with respect to the Earth-centered Earth fixed. The exam is not going to be open book, no. The exam is closed book, as with most University of Glasgow exams, Elias. So again, this section is proof heavy. So I suggest spending a lot of time kind of over a weekend just going through the proofs and making sure you understand them. But this is kind of what this tutorial is supposed to help with anyway, which is kind of more than previous years have had anyway. And again, we just need to show that we can get to this equation here with the correct terms, okay? But also showing from where our measurements come from. So that's kind of a bit that you might see, and if you look at the solutions in the tutorial sheets, it kind of explains a little bit about the gyroscope rotations. It doesn't seem to be used. This is just to show where or how we use inertial sensors to get to this equation. Okay. So to start off, we'll start off with our navigation equation. So again, in local form, you have our specific force and gravitational acceleration. Now, the first thing to note here, which is kind of the first step you'll see in the tutorial solutions, is we have the specific force currently in the frame or in the local navigation frame, and we don't measure that. So again, we measure for an accelerometer bib. Oh, got that the wrong way around. F bib. Okay, so we can therefore expand this to a simple direction cosine matrix from our bib, which we're going to accelerometer is going to measure, to the navigation frame. Okay, and then we can just pull this down as before, because this doesn't matter just yet, because it's not a measurement. Okay, and if you work kind of through this side, this will actually come to, you'll get your typical strap down equation. Again, so C from body to local navigation to NED, we're going to get B and then our typical omega. Okay, so that just sort of shows you if the accelerometer side. So we're going to leave that for now. We'll come back to it a little later. Put back. Now for our gyroscope, again, we're looking for, or we're going to get something in this format, NB. So as you can see from the skew symmetric matrix up here, so I keep forgetting that you can't see me point at the screen, where omega BMB is a skew symmetrics, which is equal to this operator. So BMB. So you'll see it as that. Sometimes you might see it as the wedge notation, which is kind of to the power of nothing. You're correct, Ewan. Sorry, totally my fault. It is open book because it's online exams. I've forgotten about COVID, obviously. So ignore what I said before. It is going to be open book. Again, that probably means proofs aren't going to be as prevalent, but it's worth kind of learning these methods because especially this proof, it comes into there's a lot of similarities between this and the mathematics section we did in the previous tutorial. Yeah, sorry, Elias, I completely slipped my mind that it's going to be all online. So yeah, we'll carry on anyway. So from the gyroscope, again, we've seen we need this rotation resolved into the body frame to do the strap down equation there. But again, gyroscopes don't measure that. So we have to step through kind of a few different sequences to get this term here. So this is going to be a combination of subtractions. So we have additions to start off with, then we're going to show that we need to subtract to get the term we want. So that's the Earth rotation. I've got the first one. We have EN, and then finally we have the one we want. Got this the wrong way around, haven't I? 2 seconds. This is going to be one step ahead of myself in my notes. So what we're measuring first, this is our gyroscope measurements. Okay. And then we're going to subtract the rotation of the Earth. And additional sort of Coriolis effects. So this is kind of what you're going to need to get to for the navigation equation from the gyroscope. So this is going from our measurements and then subtracting these other two rotations. Again, and this can be written into skew symmetric form as in this up here, but we're not really going to need that for now. For the actual proof anyway. But I'll do it for completeness. We've got time, haven't we? So yeah, so taking this, we'll put it in skew symmetric form, just so we can get this sort of strap down equation. It's equal to omega bib, so our gyro, and our other two rotations of the Earth. Okay. Again, these two equations we have 1 and 2, subbing those in, we'll end up with our strap down equation. Strap down equation is in the notes, and again, you'll be able to kind of add notes for which terms to use in the strap down equation. Okay. Okay. Right, so that's kind of a lot of the preliminary work we've just done. So we're going to now try and derive the equation that was set out in the question. Okay. So again, the final two, I think was that in the chat. I think I saw it pop flash up. The final two rotations in here, we have the rotation of the Earth, and then we have this additional sort of transport rotation. Again, that comes from when I did the drawing of the Earth and different points on the Earth. Our frame, even though it's fixed locally, is rotating. So that's why we have that third angular velocity in there. But again, not really needed for the proof. Okay. So we're looking for v dot NEB. So the body acceleration was resolved into the navigation frame or the NED frame. So first we need to define the velocity, so kind of the integral of it. And again, this is using the similar trick that, again, did people's heads in for the mathematics section. We're going to first take the velocity when it's resolved and relative to the same frame, and then just apply a direction cosine matrix to get there. Okay. Someone got their mic on? There's some creaking going on. Someone can just check. Okay, but then a very similar process to what we usually do in the mathematics section. So we're going to differentiate. Okay, which will give us is equal to c dot ne. And as you'll be able to spot, we'll need a strap down equation to solve this. We've got cne b dot eb. So we've got two terms. A different color. So if you look back to what we were given in the question, we were actually given v dot eeb here. So we're going to sub that in straight away into the equation.
Why didn't you start from the position equation and then like differentiate twice?
So we can start from velocity, just because there's not going to be so because they've got the same sensors, same origins. We can kind of show this properly.
Because usually, like when you differentiate, there is extra terms that you don't take into account if you start from velocity and then differentiate from there, or is it here fine because we have VEBE?
Because we have this already, we can start from it. Again, this, I'm scrolling the wrong thing. This would come from, because we're considering frames where the resolving frames, or the resolving axis for the velocity is not the same as the reference frame. We would have to start from the position. But again, because we have this, we can start from the velocity.
All right.
Yeah, I'll send a group email out. I'll work that out and I'll Dave why we do that, because it's something I honestly can't remember off the top of my head. But I'll send an email out once I've got the answer to that. Okay. But we're going to sub in for here. And then finally for the second term, we have kind of the where we need the strap down equation. We're going to take the form where it's in a different color. So we've got c dot ne. Okay, and we're going to take the form that has the local angular velocity and then cne. So that's the one we're going to use here. Okay, so subbing that in, it's going to be quite long. We're going to get our negative, and we get nen cne. Plus the direction cosine, and then we're going to sub in our term from up here. I'm going to copy and paste it, I think, rather than.
Did you forget to multiply by VEB?
Was that VEB, sorry? Oh, yeah, I have done here. Thanks for pointing that out. And then we have this for our term at the end. Okay. Now, the first term we have at the start is very similar to what's in the question. So we'll just kind of quickly work through that to get to what it needs to be. Okay. And it basically just we're just expanding that bracket, isn't it? I've already done it because I have the VB in there anyway. Okay, we get from there, but again, we can spot that we can use the direction cosine matrix to convert this. So we get minus omega n en, and this now turns to vn eb. Okay. We're going to do a bit more rearranging later on when we get there. Now, kind of the key thing to spot with this one, or to remember with this one, the bit of information that's going to prevent you from getting to the final bit is how to take this form here and turning it into what we want later on. So we want to get an acceleration term on its own. Find the right bits. So we can actually state, I'll go through the proof if we have time towards the end of what it actually is, but GeB is the acceleration due to gravity at a point on the Earth, defined by kind of RB there, REEB. And that's equal to our gravitational acceleration. And again, this is IEB now. Wrong way around, EIB. And then subtracting, and then we have this sort of Coriolis acceleration, which is the acceleration of the Earth. B. So this, if you remember back to sort of high school physics, this looks similar to omega squared r, the acceleration. And if you've done, I believe it was any of the aerospace modules, you'll come across this term. Again, I will go through this at the end, this sample here. But it basically comes from the fact that we can define our acceleration equal to FB plus, which we remember from the navigation equation, which was given in the question, kind of straight from the top. But we can rearrange this and get this term here. So we're going to sub that in for now, which is going to give us, I'll go down to this one here. So we have CNE, CEB, plus, I'm going to take this over. I'm just rewriting what I did. I'll sub it in now, actually, rather than rewriting. So that's going to give us. I'll rewrite that once more because there's one other step I want to add in. That's 2 omega. So we have this term, and then we also have kind of from the navigation equation this. So we're going to rearrange and cancel from these. So we've got one equation here and 2 here. And we're going to basically get, once we kind of combine these together, because through this, we can transform that into FEIB. But we're going to get the FEIB plus our kind of acceleration due to gravity that we had up here is equal to the local acceleration, f of their fixed acceleration, sorry, and then minus this Coriolis term that we saw up at the top. Okay, so again, sorry that was a bit cluttered, but again, you can use this transformation to convert to the specific force in the ECEF frame, and then from the kind of definition up here of our gravitational acceleration, we can come out with this term. So we're going to basically replace the whole of that with this here. Okay, I'll write it out a bit more neatly on the next line. So we've got everything now. Okay, plus still have that direction cosine out there. We now have minus. So these steps aren't actually in the proof that you'll see in the tutorial solutions or in the notes, which is why I kind of have done it. Okay. I missed the term up now. Yeah, this one. Minus 2 brings this one that we've got at the top that I missed. Okay. Right, so the next line, we're basically just going to expand and simplify some of the terms. So, but we've got a VNEB there. We've got a VEEB here. However, we have this direction cosine matrix. So we're going to combine these together. I'll take them out and combine them. So at least collect them together anyway. It's not a dots. I shouldn't do dots. That's going to confuse me. And then we have this negative. So this is going to be called -2 omega t. And then the NEB. So everyone see where kind of that's come from? Yeah. Okay. And then additionally in the bracket, we still have AEIB minus omega. And again, using these direction cosine matrices, we can transform the acceleration and the position terms. So here we can actually take out a factor as well. So again, just to simplify, we have VNEB. Take out the minus as well, can't we? And then the two different angular velocities. Okay, and then transforming. So applying this direction cosine matrix to the acceleration is just going to change the resolving frame. So we go from the ECEF to the NED frame. That gives us the acceleration. And then additionally, rotations, and again, changing the resolving frame to NED here. So now we're getting pretty close to, it may not look like it, but very, very close to what the solution is looking for. So if we go scroll back to the top and zoom in. So we're wanting it in this form where we have the specific force in the bib frame, because that's what we're measuring. And then we still have, we've transferred it back to the kind of gravitational acceleration as well. But you'll see that this final term is the same as what we've got at the moment for the first term down here. So this part is my green pen, this part is correct. And then we just need to work out how we've changed this. Elias, this came from, we have a direction cosine matrix here. Again, there. So multiplying these two together, expanding it out, this changes the resolving frame from ECEF to NED. And then via matrix kind of properties, you can do the same thing for this one here and change the resolving frame without having to worry about the angular velocities there. Okay. So getting pretty close there. So I'm going to rearrange the first part into the form that's actually required, just for completeness. So we have so negative and then the bracket. In an exam, if you are asked to kind of get it in the exact same form, just make sure you have rearranged it at the end. This makes it easy for the marker to go through. Okay. And then we've got this term with an acceleration and then the kind of the Coriolis acceleration as well. But if we look back up to here, we can see that it's a very similar form, except this one was resolved in the Earth-centered Earth fix. So we had FE, IB plus GEB. Okay, but now we want it in the NED. So we're wanting it in the form, well, we want it in the form BIB actually, aren't we? At first. However, because we're using the acceleration in the NED frame, so that's GNB, and we take our measurements in so the inertial frame, so BIB, we're going to put in a direction cosine to take it from wrong way around, isn't that? There we go, b to n. Okay, and that will take it into the required format that we can then use this proof, this value that we had up here. Okay. So that basically means that this equation here is equivalent to f n ib plus g of mb. However, we've not got it in a position in Earth-centered Earth fixed coordinates anymore because we're using the NED frame. We want to use longitude and latitude, or rather longitude and altitude. So that's why we add in these terms here instead of our coordinate positions. So again, I'll write that in. Plus and then the only thing we need to do again is just to change our specific force term here into a form that we use when we take measurements from a gyroscope. So that's just changing it into the inertial frame. So that means all we need to do is rewrite out the above line. We have which around b to n, and then bib, which is basically just expanding that term. Okay, which if we look at the solution, it's going to be in a different order, but again, just in the interest of time, if we go back to what we were looking for, we have the three terms that we need for the question. Okay. Right, just I know we're overrunning, but I want to go through quickly that proof of where I got this this from, which is kind of one of the keys for getting the equation in the format that's required. So I'll quickly go through that. But again, it comes from having the two bits of information that were given in the question. So we have the navigation equation here. And then, well, the second part is actually something we need to know. So I'll put a red box around it because it is important. So again, our navigation equation, so equation one that we're going to use to derive this little notation is our navigation equation in the local navigation frame, because that's the one we're given. And that's the NIB. And then secondly, the acceleration due to gravity. So whereas gamma is the gravitational acceleration, G is the acceleration due to gravity. So they are different. But it's more of a notation rather than kind of a difference in the actual meaning of them. And that is equal to GIB, EIB, and then minus this Coriolis term, which is due to the angular rotation of the Earth. Okay. So that's the two equations it comes from. Again, you need the direction cosine to change it to the local frame. But basically, we want to get, I'll change the color, the acceleration and this Coriolis term. And we have, if we look kind of the first parts, we have the gravitational and then a specific force. So we have these two terms. So again, solving them simultaneously or just rearranging, subbing them in, you can get that little kind of identity just here. So I'll note that down. So that'll come up in this one. Okay. But I apologize that was quite an involved one. You don't need to do all those steps in the exam to get the full marks. What is in the tutorial and in the notes will be sufficient. This is just kind of doing every step and every little rotation to get you to the end. Okay. I feel like it's been a bit of a quieter session this tutorial. People still there? Yeah. Okay. So that is. I'll put the question up again.
Can you share a bit?
Yeah, of course. I'll go back and share. Give me a couple of minutes.
Just the last equation you've written.
Yeah.
Isn't gamma over here IB and resolved in E, or the Earth-fixed Earth-frame, and the one above is resolved in the NED frame? So
yeah, it is. So you have to use a kind of direction cosine from Earth frame to NED frame, but it will cancel.
Yeah, so I use the direction cosine, then substitute and rearrange.
Yeah, exactly. Yeah. So again, I would probably just remember this that substitution. Again, it's not even mentioned in the notes or the tutorial solution. So because it's not in that, you still get full marks if you didn't do kind of that little proof thing. So this is, again, it's more in depth than it needs to be, but it should hopefully, I might not help you understand where it's coming from. It might have just confused you all, but that's kind of where it comes from anyway. But again, in the exam, you may get, because it's going to be a proof, it's open book and there's a lot of proofs in this section, in the initial section, there may not be as many of the traditional gyroscope accelerometer proofs, but they may change the end goal equation a little bit and just try and throw you off by that way to make it fair for people with open kind of, you can look at your notes and do it. Again, this is probably the least important topic, just based on the exam formats. The satellites and integrated navigation tutorials we're going to do in the next sort of 4 weeks or so. Kalman filters and sort of satellite navigation is going to be a little bit more important.
Can you scroll up a bit? Just I want to write that equation.
This one here. Okay. Right. Again, you'll be able to look at this after this and go through it. I just want to share the other kind of equation that could come up. So we did the local navigation frame, which is a little bit longer. The ECF one, a basically equivalent question that could come up is a little bit shorter and a little bit easier to go through. It also has that little trick in with the change in the gravitational acceleration and specific force into the acceleration due to gravity, but it explains it a little bit more in depth.
There's a lot of things you have to know beforehand, like the gyroscope measures or resolve in the specific axis, or we assume something and then continue on with that.
It is a tough course. For certain things, all measurements are done in the bib frame. That's how I remember it, just bib. Whether it's angular velocity, whether it's a specific force, that's where those diagrams can be really helpful. It shows you the resolving frames and the measurement frames that you're going to be using. Okay, so I expect I'm going to have a lot of questions with this one. So I've got my email in the chat. I believe I'll send you an email to a lot of you anyway before. So if you have any questions about anything, email me, and I'll be happy to go through kind of some things with you. Additionally, again, I would prioritize the mathematics section and then the 2 sections we're going to do next more, just because there are more sort of questions Dr. Ansel could ask where you have to calculate or do a method, which is obviously a lot easier to do for an open book exam.
Is it enough to look at like these 4 and know the diagrams for them? I mean, there's not any more derivations we could do.
So there are a couple of other things I'll quickly if you're all happy staying around for another 10 minutes, I'll go through them now. Kind of a couple of other things from this topic that could come up. But mainly it's sort of sensor characteristics, which again, it's sort of stuff you can read, but there may be, you could be asked the question, why is it beneficial to, or what are the positives and benefits of different kind of measurements, and where do errors kind of come up? So I'll do this now for you, actually, I think, because it's something, we'll have covered the whole topic, I think, by then.
Do we have to know like how much like specific gyros or whatever drift by as well?
No. Yeah, I mean, I think you could technically be asked rough orders of magnitude, but I'd highly doubt that would be a question. I mean, so,
like we discussed like a couple of errors like gyros could have, like the bias and whatnot.
Yeah, so I mean, things I would learn in from the sensor characteristics: bias, or the 4 types of error that you're going to get. So bias, you got scale factor, cross coupling, and then you have sort of your sort of Gaussian white noise, or just noise, but it just happens to be Gaussian. So they're kind of the 4 main things. Again, the simplest thing is how they notate, how they're kind of written in navigation equations. So biases are BG or BA. Their vector scale factor is just, again, SA. Cross coupling, it comes up as a matrix. So say the kind of cross coupling matrix, you get a 3x3 matrix of your scale factors. So if we do a gyroscope, for example, you get SGX, SGY, SGZ on the diagonal. And then the other terms, let me get this right around, this is MGXY, MGXZ, and then MGYX, etc., etc.
Do we have to know the derivations of these, or
not the derivations? No, but the form, yes. So again, you can look up this, copy it up in the notes, but again, it's
like
really useful.
In the notes, they just throw in equations that you can like memorize. That's how I saw it.
Yeah, in the past, that's probably been like that. However, these, especially the error formulations. So part 4 of the exam, or question 4, in the past generally has also always been a Kalman filter question. So do a couple of iterations of the Kalman filter, derive the error propagation for Kalman filter, that sort of thing. And that's where this comes in really handy. Again, you won't come up to it, but part of the end, the kind of the final bits of the course, kind of Dr. Anderson will derive a full sort of error state Kalman filter, which is, it's really important to know these errors. But again, it's bias plus identity matrix, I believe, plus the cross coupling matrix. That, because it's got scale factors in, you know, it's going to be multiplying by the specific force measured, and then you have white noise added at the end. And that's your accelerometer equation. Let me see if I can remember the gyroscope one. So again, bib is equal to, it should just be the same format, shouldn't it? That's A, that's G. Bib plus.
So we don't need to like memorize any derivations or anything. It's just the forms of these equations.
No, in some of the older exam papers in like 2013, they did kind of have error derivations in. However, I wouldn't spend time kind of worrying about that. So I would focus on making sure you can describe the errors, where they're going to come up, what effects they'd have on a sensor, and which sensors are more susceptible to which errors. So for example, accelerometers are far noisier and don't tend to have any bias, or tend to have less bias, whereas gyroscopes will generate bias and drift over time. So, I mean, those sorts of things, they may not be covered in the notes, but I would read up around them. It's kind of what I'd say for that. But really, that's kind of all of the scale factor error stuff that's kind of bolted onto the end of this topic. It's not amazing, kind of a massive thing. But learning the proofs, again, you won't be asked the proof similar to how it is in the notes, but if you can understand how to do it, especially the frame changes, that's the important bit. You could read into that and say that the gyro, so the Sagnac effect one I did at the start, and The mechanical gyro and the accelerometer aren't as likely to come up just because you can't really change those. That's kind of a very well-known, well-versed derivation. Okay. Right, unless I've got any kind of last minute questions, I'm going to end it there. Again, you've got my email address. I'm happy for everybody that attends the tutorials to use my email address and email questions because you guys have turned up. Whether it's about the mathematics section, the inertial navigation section, or the future 2 that you're going to be doing in the next sort of few weeks, just let me know if you've got any questions, and I'll arrange to have a Teams call or give you some solutions to go through. Okay. Right, if that's it, I will see you all in, it's going to be 2 weeks time, but I will send out an announcement to let you know, just to confirm. Okay.